Firstly, I would like to introduce myself. My name is Mar, a student of Hokkaido University. Today, I will present the topic fatigue analysis of UHPFRC-steel composite bridge deck, considering self-healing behavior and fatigue life shortening of rock UHPFRC under surface water condition. This is the content of the presentation. Introductions. The ultra-high performance fiber reinforced concrete UHPFRC with outstanding properties such as high strength hardening behaviors has been used as a reinforcing overlay for the orthotropic steel bridge deck to improve the fatigue performance of the kind of structure. Under water conditions, UHPFRC has high self-healing ability, represented by the highest percentage of rock closure in UHPFRC specimen. However, under fatigue loading, the reductions of the fatigue life of concrete material under water conditions has been reported in this study. The objective of this research is to develop an analytical models based on the finite element method to investigate the fatigue behaviors of UHPFRC steel composite deck subjected to moving wheel loading under surface water conditions. The self-healing behavior and reductions of the fatigue life are considered in the material model of rock UHPFRC. The analysis will be verified with the experiment from say tip-comb contraction associations. Material model of UHPFRC. After the first day under right conditions, water has been supplied on top surface of UHPFRC for 1 night before stage 2. Assume phase for material model of UHPFRC. The first phase is the self-healing of rock UHPFRC for 1 night under surface water conditions. The second phase is a higher degradation speed of rock UHPFRC under combined action of the fatigue wheel loading and surface water conditions. Stress-strain relationship of UHPFRC is shown in these figures, which is decomposed into non-rock component and rock component. In the first phase of material model, the self-healing of rock UHPFRC in terms of increasing in reloading stiffness and tensile strength under surface water conditions are considered, and the recovery ratio are chosen as 70% in this analysis, following the results of Okuzumi et al. For the second phase of material model, it is assumed that at 2 million cycle, reference stress decrease under surface water conditions, and the stress level in water conditions is chosen as 70% of that from right conditions. And the breathing stress durations applied for rock UHPFRC under surface water conditions in stage 2 can be calculated and shown in these equations. Analytical model of UHPFRC steel composite deck. This figure shows the APM model of the composite bridge deck. 7 load locations are assigned along the wheel loading lane with a load level of 100 kN. The non-uniformly distributions of the wheel loads along the transverse directions and longitudinal directions are assigned for the tire contact area. Fatigue degradation model of UHPFRC steel interface. The total expansion of 28 mm in transverse directions of the delamination area at the interface between UHPFRC and steel in this state is the same expansion speed from the reverse state under right conditions. Results and discussions. These figures show the transverse strain range result at the strain gauge SDL1 in the steel deck place. In stage 1, due to the occurrence and expansion of the delamination area at UHPFRC steel interface, the significantly increase in the strain range level could be obtained in this state. And after that, in stage 2, under surface water conditions, due to the recovery in reloading stiffness and tensile strain caused by the self-healing of rock UHPFRC, the decrease in strain range level could be observed from beginning of this stage. And after that, under moving wheel loading, due to the fatigue life reductions of UHPFRC, the increase in transverse strain range level could be obtained. In phase 2 of material model, by applying the higher speed of breathing stress duration in rock UHPFRC, an acceptable increasement in tendency from the analytical and experimental strain rate result could be obtained, especially for the early cycle of this day. This figure shows the maximum risk for strain distribution on the top surface of UHPFRC overlay, SOA. The represent are shown by the bands from the blue to red color. In phase 1, due to the self-healing of UHPFRC crack, the maximum reachable strain value decreased at this cycle. And after that, under moving wheel loading, due to the reductions of the fatigue life of UHPFRC, the increase in maximum reachable strain level could be obtained throughout stage 2, as shown in this figure. Conclusions. These 3D FEM models were performed to investigate the fatigue behaviors of UHPFRC steel composite decks subjected to moving wheel loading under surface water conditions. Due to the self-healing of 5 cracks in UHPFRC overlay, the mechanical recoveries of reloading stiffness and tensile strength from the cracks are obtained. Later, under moving wheel loading, by considering a higher speed of bridging stress duration in crack UHPFRC, the analytical strain rate result of the steel deck plates exhibits an acceptable increasement in tendency in comparison to those from the experiment. This is the end of my presentations. Thank you very much for your kind attention. If you have any questions, feel free to contact me by this email address. Thank you very much for your kind attention.